Good day, everybody, and welcome back to another episode of the Hazmat Guys. I'm Michael Monaco, so let's get into it.
Welcome back, everybody, to episode 58, and we are the premier podcast dealing with hazmat response for fire responders, where we give you the knowledge and insight to do our job safely and effectively. I am Bobby Salas, and I'm glad once again to be here with my co-host, Mike Monaco.
As always, baby, here we are, right on time.
For what? I have no idea.
Nothing. Yeah, there's really no time limit on this at all.
Yeah. Well, you know what? I want to go through a couple of things. First off, me and Mike have been talking. If you think we're just kind of sitting down and relaxing and enjoying our moderate success with this podcast, we are actually really engaged in trying to reinvent it. We've had about a year, and it's time for us to take the experiences and stuff that we've learned and really make it better. So all the stuff that we wanted to do, we're actually doing now.
We are. It's kind of really cool to, we had, when we started off, we had these kind of sets and goals of all these things that we wanted to do. And we were all like gung-ho. We were like, yeah, we're going to do like 4 shows. I'm going to talk about Instructors Corners. Bob's going to do the news and this and that. And then it was like, holy crap. It's like 8 man-hours per guy. So 16 man-hours a week just to produce this stupid half-hour radio show. In the beginning, like we were just all over the place and discombobulated, and now we've pretty much got it down to about 4 hours a guy. Sometimes it's all Bob, sometimes it's all me. We kind of go back and forth, splitting the work up, and we've gotten to the point that we feel comfortable that we can start adding more stuff and doing more and making this show something, bringing it to the next level. So for 2017, here we go, baby. We're going to be bringing it to the next level.
We're gonna, I think all the adjustments that we're gonna make are gonna be I think they're not going to affect the actual show that you're listening to. You might hear, we're thinking about changing the music a little bit, not too much. Think about the intro and all of the other stuff. But one of the things, and we haven't done it, and I'm a little ashamed, is what we're talking about right away. For this episode, and I'll give it right out. We're going over phase changes, the physical properties, some interesting stuff just to review. Really, we never really got into the granular level with this one.
No, we haven't, and it's such a foundational thing to understand.
Yeah.
In order to predict and go on, that it's really good to kind of get into the weeds. So let's, I guess, start off with the basics. When we say phase change, we also mean what? States of matter change, right?
Yeah, and this always occurs with the change in heat. Okay, it when you change phases, whether you're getting colder or hotter, you're going to change with some heat in or out. So heat either goes into or out of the material, and that's known as endothermic or exothermic. Exo is out, endo means in. Easy as that.
All right, so I think before we go on to like endothermic, exothermic, and rules and laws of thermodynamics, which is a very enjoyable topic for me, we should let's nail down the very, very basics. All right, phases of matter basic. So let's start off with a solid. Bob, what's your definition for us of a good solid?
All right, so again, guys, we know this stuff. It's in a solid. The particles are packed very tightly together, so they're basically unable to move very much. And the particles of a solid have very low kinetic energy, right? Not potential, but kinetic, meaning they want to go and do things. So the electrons in each atom are in motion, right? They never stop. Well, they actually do stop at certain points, but we're not going to get into that right now. But they're in motion, so the atoms have a small vibration, right? They're excited, but not too much. And they're basically fixed where they are. And in solids, we know that they have a definite shape. Think about wood or your table or your couch. You don't come home to a puddle of table. You have still a table when you come home. So they don't conform to the shape of the container they're in, or else we would have awesome dumpsters or trash bins because it would be a big lump at the bottom. So
All
that's
going
why
to
we
the
have
sewer.
compactors. Yeah, we have compactors and stuff. So they also have a very definite volume. We can measure this. So solids are pretty simple, right?
They seem to be really, really basic. I mean, and yes, everyone's going to say, oh, yeah, but what about, the solids that explode when in contact with water and air and all that
Blah,
crap?
blah,
Well, we're taking a very general view of all of this. So let's take a very general view. Solids are definitely one of the easiest things to deal with.
Why don't we talk about liquids now, Mike?
All right, so in the liquid phase, the particles of the substance, they have a little bit more kinetic energy to them than in a solid. And what do I mean by kinetic energy? Bob touched on it real quick. I want you to correlate kinetic energy directly with temperature. In fact, temperature is the way that we define that kinetic energy. So as I increase my kinetic energy, I'm also increasing my temperature. So just we throw around the word kinetic energy. I just want to make sure that you understand what it is that we're saying. In the liquid particles, in the liquid phase, the particles, they're not held together in any kind of regular arrangement. So if you look at salt, right, in the solid, it's fixed. It's not going anywhere. It's like it's in there. When you start dealing with liquids, you're talking about things they move around. They move past each other. They are there. They loosely interact. Some things interact a little bit more than others, but for the most part, they flow. They have a defined volume, but they don't have a defined shape, okay? So the particles of a liquid have just enough room to flow around each other, so a liquid has that kind of indefinite shape. And a liquid will also change shape to conform to its container, unlike a full solid.
And also, this is basically hydraulics, right?
Yeah.
Where compression is not an entity.
No, not at all. In fact, there is almost zero compression when it comes to liquids. You really can't crush them. You can put them under pressure, but that volume is not going to change as long as you maintain that temperature.
Interesting.
So next up, we've got gas.
Yes, the last of the three big ones, right? So you got gas particles. They have a great deal of space between them, and they have very high kinetic energy. Again, a lot of movement, a lot of jittering. They like to dance. And if unconfined, these particles of gas will spread out just about indefinitely. But if they're confined, then the gas will expand to fill its container. Now, guys, that's why we kind of change our operations versus indoor versus outdoors, because if we have an indoor or, let's say, a finite container, well, it's going to fill up the entire container based upon some other factors like heat and, vapor density and all that stuff. But for the most part, it's going to expand. But if we have an outside, it's going to basically keep spreading out until it becomes so dilute that it's not even a concern of ours anymore.
Right. And this is where we come out with the idea of parts per million, because that volume it's going to expand to that volume. So as that volume expands, your parts per million are going to go down. Right. If I have that right. It's going to go down. So it seems real simple, but a lot of other concepts are built upon all this. So really having a real good idea of what's going on, not just this is a solid, I pee out a liquid and I fart out a gas.
Right. All right. So now we've gotten through the big three, and now we're going to get into these two that you probably, I'm not going to say probably, that kind of implies that you don't know your sciences, but there are two other phases that are in chemistry, and one of them is plasma.
Ooh, the old plasma. Plasma's really, really interesting because there's a lot of high-tech science that's going on around plasma. Not something that we're going to see responding out in the open, because it's not really a common state of matter here on Earth, but it is actually really common in the universe as a whole.
Right. My plasma TV.
Oh, do you remember those balls as a kid? All right, you would plug them in, and they had the glass on the outside, and it shot out like electricity to the glass.
Oh yeah,
there was there was plasma inside that.
I like those things.
Those were nice.
Well, plasma, and before somebody gives us some hate mail, my plasma TV is not that. Forget that. Forget what I even said there. Okay, because I know somebody's going to say you're a jerk. But anyway, Plasma consists of very highly charged particles with extremely high kinetic energy.
Yeah,
right?
these are basically what happens in a plasma is you are essentially have stripped off all the electrons. It got so hot that all you really have is that nucleus, hence the charged particle, because it's not really an atom, but it's got some serious energy going on to it. And because of that, you can manipulate it with electromagnets and all that other crap that they use in science. The ones that are really big, like if you were going to say, hey, what are the common plasmas that we use? Helium, neon, argon, krypton, xenon, and radon. Those are the most significant ones that are used all over the place, and that's where we get neon signs.
Neon signs.
Neon signs. So the neon signs come from this concept of stripping off electrons and throwing them back on, and plasma running around. And stars. Stars. We get our star. We get all of our energy from stars, right? Because the sun is a massive incandescent gas, a giant nuclear furnace, turns hydrogen into helium. No, you don't know that song?
No, never heard it.
Really?
Who did that? Is that There Might Be Giants?
Yeah, There Might Be Giants. The sun is a gas.
Oh my God.
Yeah, it's a good one. Check it out, guys.
That's good.
We'll talk about it the next one. And now, if we flip to the exact opposite of a plasma, we've got...
Well, we have Bose-Einstein condensates. What?
Ooh.
That's crazy.
Like the stuff that forms on my
all right.
glass in my beer, the condensate.
This is one of those ones that is very, very interesting, and it is definitely a phase, although we will not see it. And some of you out there are shaking your heads going, what the hell are these two jerks talking about plasmas and Bose-Einstein condensates and chemistry? But remember, just like we say at the end of don't just get on the job, get into the job. These things you may not see on the streets, but in order for you to not only sound intelligent, maybe speaking to somebody, one of your peers, but also to maybe make a buck at the bar when you can sound really awesome and get a free beer sent for you.
Yeah.
That's game right there.
Yeah, or just kind of giving that little bit of information that makes you sound like you know a hell of a lot more than you actually do, which can lend you a tremendous amount of credibility when you're talking to a chief and you're trying to convince him,
Right.
That's
What are you guys doing over here? You know what, Chief? We're just trying to keep the Bose-Einstein condensates down, and then we'll be good. We could take up. Oh, okay. You sound like $1 million.
Yeah.
You really don't know what you're talking about. But in 1995, technology enabled scientists to create a new state of matter, and this is called the Bose-Einstein condensate, which is the BEC. And what we do is we use a combination of lasers and magnets, and this is actually the guys that did it was Eric Cornell and Carl Wyman, and they cooled a sample of rubidium. I put the emphasis on the wrong syllable.
like rubidium.
rubidium, to within a few degrees of absolute zero, which is what, negative 276
270, I think 273, yeah, 0 Kelvin.
273?
Yes, it's low.
It's low. It's
really
super
low.
low.
Really, really low. And at these insanely low temperatures, the molecular motion that we were talking about with the gases and the solids and the liquids, it all comes to a standstill. All right? On a molecular level, they are frozen, literally frozen. They stop moving altogether. No kinetic energy is transformed from one to another. And the atoms, they do this crazy stuff. They come together into this giant mass of... They act like one atom stuck and clumped together. There's no longer thousands of separated atoms. It's just this one big, giant superatom.
Wow.
Yeah.
Well, the BEC, the Bose-Einstein condensate, is used to study quantum mechanics on a macroscopic level, and the light appears to actually slow down as it passes through these BECs, allowing a study of particle and wave paradoxes. So the BEC also has many of the properties of a superfluid, flowing without friction. So it's even though you think frozen, this is frozen beyond recognition. This is frozen so much that it actually flows like it is made of grease, and it is used to stimulate different conditions that might apply in the black hole. Yeah. Pretty cool.
Crazy stuff. So, do you need this out in the field? No, absolutely not. But you know what? We're kind of nerding out a little right now, so
Yeah.
we just gave you a little bit of information. Uh, let's head back. We're
Okay.
digressing too
Let's
far.
go back.
All right, let's go back to our states of matter and really the science. All right, the stuff that is interesting to us is not necessarily the solid, the liquid, the gas, but it's this point where we change phases when we go from one state to another. So from a solid to a liquid, or a liquid to a gas, or any of those combinations, without affecting the chemical state. In other words, it's the same chemical. All right, we haven't had a reaction. We just had a phase change.
Right. And generally, this also accompanies a change in the volume of the matter, right? I mean, if we go from a solid to a liquid to a gas, we're basically in that move, we're expanding.
Right. Absolutely. And if we go from a gas to a solid, then we're going to be occupying less volume. So we're going to be contracting.
And of course, there is one common exception to this. It's water.
Yes. And without this common exception, life on Earth could not happen.
Right. Yeah. So this temperature will affect both potential hazards and our moves to secure it, right? So what do we got first?
All right. So let's probably one of the more interesting. Well, I would say there's only really two phase changes. So the first one is going to be melting and freezing. Let's chat about melting and freezing a little bit.
All right, we can talk about this. This is called, the first one we're going to talk about is melting point. And this is one of those quote unquote critical points to note when dealing with hazmat. This is one of those things that we really need to know what it means. Melting point.
Yeah, because something as simple as the time of day or the weather or what's happening inside a building can all have dramatic effects.
Now, Mike, I would like to say that in general, it's a lot easier to deal with a solid than a liquid, right? I mean, I can sweep up. I can throw very easily into a container, whatever a container might be, a solid. It's very, there's almost no associated volatility. There's all this. It's really easy to deal with a solid. Would you agree?
Oh, absolutely. I mean, just from all the things that we know about, like you said, the table before. I know this table is not going to melt. If I come back here tomorrow, the table is going to be in the same place. It's not going anywhere. It's not doing anything. Like, I can predict where it's going to go. If I'm outside and I'm on a hill, I know the solid's not going to really move unless it's on a wheels or something. So yeah, it's a real comfortable thing to work with.
Right.
Whereas,
what about a freezing point?
What about the freezing point? Well, it's really just it's the same as the melting point, but going in the other direction. Right? So yeah, it's if we think about the point at which something melts, it's heating up from a solid to a liquid, and now we're just gonna go opposite.
Okay, so in this one, we're basically going from the liquid to a solid. We're freezing things.
Right. They're I guess we can't say everything, because there are some things that they don't quite work like that, if that makes sense.
Like
supercooling. Like supercooling. All right. When we supercool something to the point that it freezes, it doesn't necessarily coincide with its melting point. So, for example, if you YouTube super cooling liquids, you can take a Poland Spring bottle, stick it in a freezer, drop it down below its freezing point temperature. But because that water has nothing to bind to, nothing to form a crystal, which is a solid, it's going to stay really, really cold. Now, you take one little particle, one little speck of dust, and you drop it in there. The water now freezes to that crystal, to the particle, creates the crystal, and you see this massive crystal expansion, and the whole thing freezes at once.
Wow.
But before it does that, it is literally well below its freezing point, but still a liquid.
Interesting.
Yeah.
A little nugget for you home nerds.
Little science. Yeah, we got a lot of nerd pull-off points tonight, if you know what I mean.
Yeah, it's awesome. All right, well, let's go up to boiling and condensation. First, let's go into the boiling point. What do you got?
All right, so this is where the vapor pressure equals that atmospheric pressure that we hear about so often.
Okay, so the definition of a boiling point is the temperature at which boiling occurs under the pressure of 1 bar. And they always use 1 bar. Of course, there's equivalents of 760 millimeters of mercury and, was it 14.7?
Yeah, 14.7.
1 atmosphere.
1 atmosphere.
It's blah, 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 whatever you want to use. But it's all basically saying it's when the temperature of boiling happens under that pressure.
Now, this leads to some really interesting science because there's something called the heat of vaporization, which is the amount of energy required to convert or vaporize, all right, because that's what we're literally trying to do, a saturated liquid into vapor.
Okay. And now we know, all right, well, where I live, water boils at 212 degrees Fahrenheit, which is basically at sea level. I live very close to sea level, and changes slightly based on locations, and slightly is a couple of degrees.
Right. And this is all, based on the atmospheric pressure on the water. Like Bob said, we're talking about standard temperature and pressure.
All right, so as you go up in elevation, there's less pressure, and so the amount of heat needed goes down.
Right, so the point at which water boils at 5,000 feet is going to be something like 203 degrees Fahrenheit.
Wow.
So it's significantly less. That means that literally the water is colder and still boiling away.
Right. And we also know that adding pressure will affect the boiling point of things, right?
Right. So if we put our liquid in a pressure cooker, it's going to raise up that point at which it's going to turn into, go from a gas to a vapor.
What if we add salt?
All right.
Something like, whatever. Just table salt to, things.
Table salt. All right. So there's actually kind of 2 things that are going to be going on. The first is it's going to elevate the boiling point. All right. So we added the salt to it. And this is going to be true with anything that's dissolved in a liquid. You're going to increase its boiling point.
Mm-hmm. Any impurity doesn't have to be salt. Any impurity will raise the boiling point. And this is like one of those cooking wives' tales that if we add salt to the water for our yummy, yummy pastas, that it will cook faster. And actually the difference is very, very small, pretty much insignificant.
I actually had, so going along with this wives' tale,
yes.
In high school, I had a friend. I'll give a quick shout out to my friend Vic. And we had an argument over this. And she's like, no, I'm telling you, I'll take the salt, I'll put it in the water, and it will start to boil. Okay? But and she was kind of correct, and I was kind of correct. If you bring water up to like 205 degrees and you pour salt in there, you will start to see bubbles forming. And the only reason that bubbles are forming is because now the water vapor, just like in the supercooled liquid, has something to attach to and is a point of vaporization. So you will start to get bubbles, but you are not at the point that the water is ready to release itself fully into vapor. So that's where the that's where the wives' tale comes from.
I like it.
Now, there's something very interesting that happens with going from a liquid to a vapor that doesn't happen going from a liquid to a solid, and that is that the liquid is always vaporizing, which means that liquids may change to vapors at points lower than their boiling point, and we commonly know this as evaporating.
Right, and evaporation is basically it's a surface phenomenon, right, in which molecules at the surface of the liquid escape in the atmosphere as a vapor.
Right. However, the evaporation rate is the amount or the speed at which those molecules are moving from a liquid to the gas. So then really, Bob, what is the difference between boiling and evaporating?
Well, evaporation only deals with the stuff at the edge of the liquid into the atmosphere, where boiling is more of a process at which molecules anywhere in the liquid will escape. And we've seen this, right? We see the pot of nice clear water, and actually not too long ago, my son, who is 8, says, how does a bubble go underwater and come to the top? I said, it's a really good question. What you're seeing is boiling, not evaporation. and we got into that, and we started, he started grilling me really hard on the Bose-Einstein condensates, and I said, listen, you got to back up. You're only 7. You don't need to know about this stuff yet, and then he started shooting plasma and stuff.
It's like a language. They grasp that quantum mechanics at such an early age.
Oh,
it's amazing. It's so sad they don't teach this stuff earlier on in life.
No, yeah. Well, he had to get his smoking jacket on with the elbows sewn in and go teach for a little while.
All right. So if we have the boiling and we had the evaporation, Bob, what is volatility?
All right. It's another term for evaporation, right? Some liquids evaporate much more readily than others, right?
Right.
So when a liquid is changed to a vapor, it's called evaporation or vaporization.
Okay, so when a liquid readily changes to a gas, that means it's volatile.
Right, because it doesn't need temperature to do it. It can do it at normal temperatures. You know what I'm saying?
This is one of those terms that I think a lot of new people get confused with, because the word volatility is thrown around so much as like something that is extremely reactive. If you ask a new class, what is volatile, they're going to tell you gasoline, dynamite, napalm, and they're thinking like big reaction, explosion, and it's really not. It's just a simple term for how much a liquid wants to be a gas.
Right, and it's only at the surface. You know what I'm saying? It's only at the surface. So, and this isn't even part of the outline, but if you increase the surface area, then you increase the volatility.
Oh, which is why when you have a spilt like a water and you mop it up and you spread it across your floor, it evaporates so quickly.
Yes. So that's why if I have a test tube of, let's say, acetone, which is a volatile, liquid, it will take maybe a couple of days for it to go. But if I take that and spill it across a table, increasing the surface area, increasing the area for it to atmospherically volatilize or vaporize or whatever the hell you want to call it, it will go very quickly at a normal temperature. We're not boiling it. We are vaporizing it. We're volatilizing it.
So let's now go backwards, right? We kind of went from solid, liquid, gas. Now let's shoot the temperature back down. We're decreasing the temperature, and we're going to start to see the vapor returning back into a liquid. This is something that we call condensation, and it is literally the vapors or the gas dropping back into liquid phase.
All right, let's get into sublimation. I love this. Everybody's favorite buzzword, sublimation.
Great band.
No, they weren't. You're too kind. So what is it?
Well, this is when the material converts from a solid straight to a gas without any interference whatsoever. So there's no middle phase. There's no liquid. There's nothing to get wet like in dry ice. Hence the term dry ice, because here you have a block of carbon dioxide that never actually gets wet.
And another example is iodine, and this one actually travels until it finds a nice cool spot to condense once again. It doesn't like to be out there in the gaseous world, apparently.
Yeah, it's like a hermit. Iodine is like the hermit of the elemental world. All right, let's hit a few what we like to call critical points. These are some things and information about this whole process that you as a hazmat technician really should know. So, critical temperature. Let's start off with that. This is the minimum temperature in which a gas cannot be liquefied, no matter how much pressure is applied. Now, this is really key. And listen, if you want to know, in this day and age of technology, you can just type in, methane critical temperature. But if you don't have that, then you need what's called a compressed gas handbook to really give you this pressure temperature curve. Why this is so important to us, because if you have a liquid and you have it contained and you have reached a point at which nothing can hold that product from becoming a gas, what's going to happen?
Boom.
Boom. You have a BLEVE. All right? So the critical temperature is something that's really, really important.
Wow. Wait a second. You said Blevy, and that's a throw around word as well. Can you have a Blevy in, let's say, a water extinguisher? It's not a chemical. It's not a hazardous material. Can you have a Blevy?
You absolutely can, and I've actually been on jobs in which that has happened, where the roof man dropped there. We had a top floor fire. The roof man's extinguisher went through the roof, and there was a few minutes later, there was an actual explosion sound. And when the fire was all put out and said and done, we found a pressurized water can that looked like it had been filleted open. It literally blevied.
Interesting. So it doesn't have to even be a hazardous material. It just has to have that expansion within a closed vessel.
Yeah, you just literally need a boiling liquid to expand into a vapor.
Another one is critical pressure, and this is basically the pressure needed to liquefy a gas. When we take that liquid and we're going to squeeze it down and make a liquid.
Right, and there's actually a critical pressure associated with every temperature range as well. And this is where we start to get into our cryogenics and the pressure curves and that whole 9 yards.
Interesting.
The next one, that doesn't seem like it's important until you open up a hatch that has been involved with fire and it flashes in your face. It is known as the auto-ignition temperature. And this is the lowest temperature at which a substance will ignite in air when there is no ignition source. All right? And we see these when we see like diesel trucks involved in fire. All right? Where the fire's impinging on the tank, the diesel heats up, the fire goes out, somebody goes up to, just check on the diesel, opens up the hatch, that diesel now mixes with the air, it's above its auto-ignition temperature, and whoosh.
That's it. And there he goes.
Crispy
We've seen
critter.
these videos. How about the SADT, the self-accelerating decomposition temperature? This is the temperature above which decomposition of an unstable substance will continue unimpeded regardless of the ambient or external temperature. Let me explain what I mean. This is the time where, this is the point, actually, at which something that's ready to go is going to go, whether you like it or not, whether you try to stop it, whether you try to cool it, it's going to go. And so this is a very dangerous point in a lot of chemistry. You're going to see this mentioned a lot in fixed facilities where maybe they have different mixing tanks or whatever like that. They're going to have different SADT points, and they have to keep that. So you might see perfect example. You have to keep certain things cool, right? So
like
these
peroxides.
things is like peroxides, right? And we're going to get into that in a second, but you have to keep them below this point, or else you might have rapid decomposition, rapid changes that might be exo or endothermic that you do not want.
Right. And before you purists start to go throwing us, hate mail, yes, we are aware that the self-accelerating decomposition temperature and another topic that we're going to hit on in a second are not technically phase changes, as we were talking about before, with the same substance going from a solid and a liquid and a gas, that it is a reaction type stuff. But it is really important stuff to know, and it does involve a liquid going into a gas. So we figured it was a pretty good spot to throw it in. The next one that we want to talk about a little is the maximum safe storage temperature. This is really more of like a building inspection type of an issue, where it's the maximum temperature at which this product can be safely stored. All right, especially when we're dealing with the peroxides and the oxidizers, this temperature is usually well below the self-accelerating decomposition temperature.
All right, and then we have the last one, which is polymerization. Everybody's fan favorite. It's awesome.
It's great.
We did a whole show on this. If you want to check it out, go to the hazmatguys.com/THMG030. That's episode 30. We did a whole polymerization thing.
That was that one of our award-winning episodes?
That was a double bond award winner.
Yeah.
I still got that plaque on the wall. It's very...
Yeah, we were very proud of that one. That was actually one of our that was our fourth or fifth one. So we were excited about that one. And if you are too lazy to go and look up that episode, which you're only doing yourself a massive disservice, this is where a special chemical reaction that involves things called monomers, they're going to react with themselves to kind of form these really long chains of chemicals that are basically unstoppable once they start. So
yeah.
If you weren't going to listen to it, hopefully that's a little bit of a teaser to go and listen to the episode.
Yeah. Well, that wraps up another episode of the Hazmat Guys. Thanks for taking a little bit of your day to listen to us and hopefully make your job a little bit easier.
And if you want, you can find us on the Facebook, or you can find us on the Twitter. All right, either one of those. I know we're entering new technology. It's the Hazmat Guys, so just jump onto either one of those and take a look. You can also find us on Google+. We used to tell you to leave a great review on iTunes. Screw iTunes. Tell a friend about us. That's the best way to kind of spread the word, is just tell a friend. Makes a great Christmas gift. Stocking stuffer.
That's all right. You can call us on our hotline at 843-628-1484. And also, we are recording the show and also producing a live and unedited version of the show on YouTube every week. So you can find us at Google+, and also follow us, and you can be notified when the show starts if that's what you want.
We are always looking forward to your feedback. Let us know if we're doing something interesting or you want to hear something. We also want to know about interesting incidents that you were a part of. Please don't sit there and think, oh, I was on an interesting incident, but I'm not, some crazy specialist, so they're not going to learn anything from me, because I'll be honest with you, we're not really crazy expert specialists either. We're just trying to learn from one another. So send us a note at feedback@thehazmatguys.com.
And remember, guys, don't just get on the job. Get into the job.